Even better? All right. So today I'm here to talk about the current Heroku approach to durability in a cloud environment, as is sometimes called. But really, a lot of lessons could be applied to any sort of environment. I really think some of the trade-offs we've made will be useful even in dedicated data center environments in the future. So I just wanted to expose this to the Postgres community and hopefully attract some contributors as well as kind of get people thinking about this problem. So here are some critical statistics. First of all, this slide presentation is actually on the web. I actually recommend you go there to follow along and skip around, especially if you are like an advanced user who understands Postgres recovery very well. You might just want to quickly hit the README the moment you see this link and just start poking at it. Also, if you have any questions or want to contribute, there is my email address. And basically, this is all the critical statistics on the second slide. So at this point, you really could leave if you really wanted to. But I thank you for humoring me and staying around. So here's the big picture that I want to expose. First is, what is this thing, and why did I write it, as opposed to reusing some other software? And then also, what's the mechanism? What is the intuition around how this whole thing basically works? And this is sort of an introduction to how Postgres recovery and write-ahead logging works in a very condensed format, just enough to kind of get the idea. And some of the strengths and weaknesses of the approach that WAL-E takes, in some ways it can be contrasted to these continuous archive utilities that have been around in Postgres since version 8.3 a long time ago. And finally, kind of putting it all together into one sentence to understand what is the thing that we're targeting exactly in a very condensed format. Then I'm actually going to switch gears and talk a little about the technical details. This is the heckling section where you can embarrass me. And just this is a good Q&A area where people might ask for details around like throughput or what are interesting problems or anything like that. But just to kind of whet your appetite for those kind of issues. So I kind of broke it apart into two parts, the high-level part that's about what is the philosophy, and then the technical part. So it's kind of two conclusions, and there's two pieces. So first is the what. That's actually one of the easier parts. It's a piece of open source software under the BSD license. It's used at Heroku to protect our greater than 150,000 databases. It's on every single Postgres installation. It's basically the first and not last, but our preferred defense against data loss. And we have used this more than once to basically recover totally destroyed disks, which do happen. Our infrastructure provider only has a certain amount of block device guarantee, and they do hit that target. At some point you will lose it, and you just got to be ready for it. And it's never good to tell a customer that, sorry, you have to lose 24 hours or a week's worth of data. That's just not really a very pleasant experience, and we prefer to avoid it. So we wrote this tool to meet this exact need. Also, we wanted to enable replication, a long-standing feature request on the Heroku platform. And as it turns out, getting a copy of your data for disaster recovery looks a lot like getting a copy of your data for replication. And that's really handy because our disaster recovery is constantly tested by people making replicas. And for that reason, I do feel fairly confident about the way data is persisted on our platform. I really feel we've done a very good job, although we do intend to do better. Our imagination has some more limits that we can reach. So why did I write it? Why not just grab a piece of existing software? Well, durability is really important to us. OK, I kind of repeated a few things. One major feature is we have to organize a lot of databases. And this is something which is not super well met by some of the existing entrants in this space. For us, because there are so many databases and so many database instances, we need to be able to organize all of our databases in a very lucid way, and especially avoid this very subtle problem of overriding your write-ahead log segments. I'll get into what that means later. But we need to make sure that every single instance is very neatly contained and it's very easy to audit whether we have made a mistake or if there's been any bugs. And so there's a very controlled interface that prevents you, hopefully, from making this mistake and having a nice, easy way to check for mistakes. That's really a big feature, and it also limits the flexibility of the tool just a little bit. So one other big thing is that the most durable storage is non-conventional file systems. at least for us, and I think it's really true for most people. Basically, the interfaces provided by, say, your vanilla Unix file system are too wide, in a sense, to actually distribute and scale and make durable in the general case. And for us, the solution to that has been this thing called object storage, which is realized in Amazon Web Services S3 service. And to the best of my knowledge, I keep on searching for it because people tell me, I think I heard it happened, and then I keep searching for it, and I never actually find any reports of it, is that it's never lost any committed data. Whenever you have put to S3, to the best of my knowledge, it's never corrupted or lost anything ever placed. That's not because it's magical pixie dust. That's because in some ways it's a pain to work with versus regular Unix file systems, and there are certain properties it has that basically make it amenable to wide-scale dissemination of data at the expense of the ease of mutation of that data. That's kind of the long and the short of it. But this kind of storage is popping up all over the place. There are going to be, there already exist open source implementations that people could install in their data centers, and I think in the future that in the enterprise or anywhere else that it's basically the new tape. It is effectively gas-powered tape, and I think it's going to be deployed everywhere as soon as the software to do it standalone is mature. So this is the final statement of requirements. Designed to archive 1 million databases, to make administration feasible for deployment of that size, providing cohesion of the software at the cost of flexibility, because it's our use case for us fighting with some pre-existing software, such a linchpin of our infrastructure, may not be worth it versus just writing something that does exactly what we want. We also happen to believe that it's what a lot of other people want too. That's why it's open source, and we think it's simple enough that people want to use it in small installations too. And finally, it can't be expensive, especially in man hours. It basically has to take care of itself. You have to be able to install this over and over and over again, and pretty much it can't bother you most of the time. And that's actually a critical feature for us that disqualifies a lot of technologies, because if something requires a lot of hand-holding, it's basically impossible to run as a service and impossible to deploy at such a large scale. And that's something which this tool so far has met the requirements for, and will have to continue to meet the requirements for as we continue to develop it at Heroku. So now I want to switch gears kind of into the mechanism, sort of the meat and potatoes at the high level. That'll be the deeper one later, of how this all works. But we want to start with Postgres. There's two major components in Postgres in terms of where major data is written. And one is in the kind of the main data files. That is where you query everything. So when you do a select statement, it actually goes against these data files. But there's another thing called the write-ahead logs, and this is in the pgxlog directory, which often people actually put on a different disk. And that's the thing that gives you crash recovery. And to explain what this is, the write-ahead log captures every change made to the database. This is a feature that's been around since like 7.4, some very long time ago, and it's been expanded since then. In particular, whenever you commit any writes, the guarantee is not that it's actually been flushed to the data files, but it's been flushed to this write-ahead log, hence the write-ahead. And it's sequentially written, constantly appended, like a log, hence you get write-ahead log, the WAL for short. So that's kind of just to give you a sense of how this all works. Every database state that you've ever written can be described as the initial database plus some amount of WAL. This is kind of the fundamental observation used in log shipping and streaming replication technologies. It's a very powerful abstraction because it allows you to move around changes to the database that are constantly appended, and that just gives you a lot of power to do point-in-time recovery and recover from disasters and so forth, mostly because you don't have to mutate some existing piece of data. You just keep on adding more instructions on how to get to where you need to go. So now I'm going to move on to actual WAL-E stuff. There's only 4 operators. I tried to keep it as small as possible. As you see, there's 2 write operators and 2 reading operators. And there's 1 for WAL and 1 for backup. 2 by 2 is 4. That's how I got 4. It's very systematic. So I'm going to address them 2 at a time because there's some similarity. So first I'm going to start with things grouped by write. This is what runs on your live important database. So first there's WAL push, which archives every single WAL segment. And this plugs directly into a configuration option called the archive command. If you want samples of how to configure that, you can look in the Postgres manual, but also there's a little cookbook in the WAL-E README that will just help you out. And there's backup push. Now, you need to do one, because if you have no initial base case, you cannot possibly derive the changed cases. But you're probably going to do one, and you probably want some more, because otherwise your recovery time will be disappointing, would be the right word. So you could do it daily. Another interesting metric would be by number of segments produced. That actually is a very good heuristic, we think. The ideal would be, if you want to have even spacing for disaster recovery, how expensive every WAL is to apply. But that's actually like a core feature to estimate that. So I would say just go with the number of segments, or if you have no disaster recovery at all, please just use daily. It's better than nothing. And that's pretty much all you need to do. And then on the fetch side, you grab something. Backup fetch downloads, possibly a lot of data, hundreds of gigabytes, maybe terabytes if you're big enough. And basically, in order to reach the present, the more recent it is, the faster your catch-up will be. But you can keep old backups around to do point-in-time recovery to enable forms of time travel and auditing. In some situations, it might make sense to never expire data. If you don't want to build auditing into your application, but you need every single transaction for some strange reason. And then finally, there's the part where you have to download the WAL segments. And actually, Postgres knows what WAL segments it wants to get to continue recovery. And that's the WAL fetch, which is just plugged into the restore command. And so that's it. That's basically all you need to know to run this in maybe a couple of minutes. So the main strengths of WAL is that it's really simple. Some people in the wild who basically use it, even though I haven't done too much advertising, simply because there's not much you need to do to get it to work. Right now, unlike a lot of software, it organizationally kind of scales down to the one-man shop as well as to something as big as Heroku. And that's something that I'm proud of, and I hope can stick around for a while, hopefully forever. But that's something that's fairly rare. It's something that can be used in a small deployment as well as a very large deployment. Also, unlike all the other archiving utilities, I don't want to name any names, because actually there are some very good ones out there. Object storage is the priority, and that requires some interesting trade-offs in order to get good throughput. And I want to support a file-based mode, but it's always going to be a priority to support the object storage abstractions above those. And finally, it's battle-tested large deployment. So at the very least, you can say, hey, it's been running on like who knows how many thousands of servers. If I find a bug, I'm pretty special. So at least you can say that if anything goes wrong. So far, it's been OK. So the weaknesses. This did start life as a quasi-shell script. It never was a shell script, but it kind of looked like a Python version of that. It has some rough edges. As long as you check your return codes, you probably won't do the wrong thing. But I won't say it has the best error reporting in the world. I'd like to improve that. There's some important optimizations I haven't implemented yet, especially to speed up recovery time. It's not as flexible as some of the other options. A lot of the Postgres tools beforehand were written to basically acceptably satisfy every use case, whereas this thing says, I know, or I don't have any way for you to control where to put anything except for one option. And basically, unless you're a contributor or the maintainer or the author, you have no options, sorry. That's kind of a cost, but it also keeps the software really easy to configure and install, and also just it allows us to we basically are trading flexibility for the ability for the time to optimize some of the recovery, recovery time, which would be considerably harder if you had configurable ways to put everything everywhere. And finally, although I really want to solve this, it doesn't yet support file system storage. And the reason for that is because, well, one, writing an agnostic abstraction layer is sort of a pain. I want to get there, though. And I really want to get there because I think that there's a lot of places that have a very reliable, like Samba cluster or something like that, that would benefit from this tool, even if they're not on Amazon Web Services and have a fast connection to S3. And also, it'd be great for testing, which is, besides Heroku production, a little bit thin. Painful admission. So to kind of conclude this overview, the whole point of this tool is to enable extremely robust replication of all your data and to have a very well-oiled disaster recovery playbook with very minimal fuss overall and especially per server. That's what this is all about. All right. So now that was probably pretty fluffy for a lot of you. So what have I really done? What actual work have you actually accomplished? So first, let's talk about the constraints. So what's the problem with object storage? You don't get any really fast random access. You can't just call seek and then write and then put stuff anywhere you want. That's just really slow. You have to upload entire keys at a time. And there's cost to every key, so there's some trade-offs you need to make there. You have limited bandwidth per connection. Every connection you make is some HTTP load balancer. It has finite bandwidth. The plus side is, because it's stateless, you can get a lot of them. So that's an anti-constraint, is that you can parallelize if you design your archiving format correctly in order to get many, many load balancers helping you out when you really need to get that data quickly. The other interesting constraint is even though it's often modeled this way, object storage is not a hierarchical file system. There is no directory inode where there's a stat where you can actually look at what's inside this directory very quickly. It's actually usually just key value, and the only kind of indexing you really get is prefix matching. Which is very interesting because if you put anything as a suffix of any key, all of a sudden your ability to scan it quickly really degrades. For example, extensions, .json or .zip. If you want to identify zip files, unfortunately, it's really hard to do because there's usually no suffix matching. Interestingly, you're probably better off if you want to know the type of the file, zip dot, and then your name. So that's an interesting thing, and I've actually made a little design error that I hope to rectify soon that slows things down a little bit because of that. So that's an interesting thing that you don't usually see in standard Unix file systems. Anyways, it's a slightly different world. There's also network block devices. Interestingly, because if you're all network connected to your block devices and your object store, your access to both competes for bandwidth. And it's really painful from the throughput perspective to materialize any extra files on disk that you don't need to materialize. This is kind of a big deal because if you buffer things to disk and then untar things in the kind of naive way, then you're kind of burning a lot of bandwidth because you write it and you read it, and then you write it again. And that's just, normally that's kind of considered to be free, especially when you have 2 RAID arrays or something, but for us it's definitely not free. We have to pipeline decompression directly out of the object store, and that just improves throughput by a lot. Also, on network block devices, much like standard block devices, sequential reads have a lower impact. That's actually not uncommon for many kinds of storage, but it is interesting to note that surprisingly, just reading the files with something similar to CP is actually pretty low impact. You can do it on a pretty busy system, and the effect is measurable, but usually not catastrophic. It's interesting to know. So the general goals are we want to exploit parallelism of the object storage layer. We want to avoid random access and minimize moved data, just basically to make everything as fast as we can implement. So some techniques that are currently implemented and I would like to implement. So first thing is compression. All data is compressed because you don't get that much bandwidth, so you may as well use it wisely. Unfortunately, you also want to keep CPU usage low. So right now, WAL-E only has one archiving option, LZO, which is really fast, but kind of on the less intelligent side of getting things to be really small. You only get maybe, like this is actually an order of magnitude number. It's not 200 and it's not 1. You get like 20 to 50 megabytes per second, so you better use it carefully. And one way to double your channel capacity, I've seen the average case, is to use compression. For LZO, I would say very commonly the compression ratio is 2 to 1. On backup push, we do uploads in parallel. And one interesting aspect is we actually go through and scan the tree of all the files in the Postgres directory, and we statically choose what volume they fit into in the upload. So that way, there's no files that span between 2 volumes. This is actually very important for the download step, but it also lets you parallelize the upload step. we also write a little bit of metadata to signify what position this backup has in the stream of WAL that construes all of your history, and also if this backup actually finished successfully. There's a Sentinel file that only appears in the event that everything has gone exactly correctly. And you can have partial backups, and WAL-E will not just let you silently do the wrong thing. It will always check for the Sentinel file. Most importantly, this disjoint tar archiving thing allows you to do parallel download and distributed and disjoint unpacking to the data directory. So in that case, you can have, say, 10 downloads going simultaneously of 10 volumes, and then you can just have 10 untar processes going at the same time. And this is why I couldn't use things like parallel gzip or anything like that, is I can't seek around the file and do fast things with the archive. So instead, I basically am paying a little bit to duplicate the tar headers so that I can have, say, 100 complete tars, all of which are known not to clash with one another, because I planned it that way to begin with, and I can just blow them all to disk as soon as I can. And most importantly, this approach avoids having to dump the archive to disk and then having to unzip it. I can just directly grab the tar from S3, and without ever putting it on disk, I can just put it onto files that are the uncompressed Postgres-compatible form right away. And that saves you one big cycle that would otherwise be spent in a very simple implementation. So this is probably the best story I have to tell. This is the most optimized part of the process, because getting those base backups can be very large, and if you're in a disaster situation, you don't want to wait too long. Unfortunately, the WAL fetch and WAL push are pretty dumb. They basically just grab a WAL segment or upload them. They do compress them, but it's an interesting, if you ever dealt with archive command or restore command, then you will have noticed that you get called one at a time with restore command or archive command, and basically the Postgres archiver does not know anything about parallelization. And I'm going to have to do something about this. Maybe not in the Postgres archiver, because I'm not even sure what the right trade-off is, but I'm going to have to figure out how to pipeline and parallelize this aspect of recovery, and also when you have a lot of writes of archiving of WAL segments. So that's an area for active improvement, but it does work. It's really simple. The code's not hard to read, I think. OK, so now here's the real juicy part where I get you guys to actually submit bug reports and patches, and also to use it. The target I have as a personal goal is you should be able to deploy this tool with some fine print within 15 minutes. You should be able to just kind of pick it up, go to the README, and get it installed in 15 minutes. Fine print. If you have an easy time with dependencies, you'll have a tough time on Red Hat 5, for example. Sorry. And you have S3 credentials. So if you're somewhat familiar with Amazon Web Services already and have the account. So I can't take responsibility for making their sign-up process easy, but I try to make sure that the part that I can actually directly affect is really short. And this is important to me because I really do think that this is an important level of durability that really almost everyone ought to have. So first, read the README. It's not the best README, but it's not terrible. I do want to make a proper manual. Right now, Heroku runs this with Python 2.6 and 2.7. I think it could be backported to 2.5, which is kind of the standard old Python now, but I don't do it, so I can't vouch for it working there. On your hand, you can be guaranteed there are many installations on 2.6 and 2.7. If you're not a Python person, you should look at virtualenv to get some of the dependencies, and there's also some dependencies written in C. These actually can be pretty old, so that's not the most critical thing to have the newest of, but there are some new Python packages that I need. So dependencies might be the ugliest part of this. The configuration is actually it's really simple because of I've said this several times, but this is actually how simple it is. You need two things. There's a storage prefix, and you see here it's s3://mybucket/a database, and the credentials is right there. That's the only configuration that's absolutely required to actually use this tool. And that's actually been attractive to a lot of users, that they don't have to think about where to put the base backups versus the WAL. It's just all managed by the tool. You can just see it as liberation or fascism. You can choose which you want to interpret it as. Then you have to set up the Postgres configuration. You need the archive command. There's a cookbook in the README. Then you have to do a backup push, at least once. Again, that first one. And then you're done. Now you can start actually hacking code or something. Please report bugs and stack traces. Certainly some error handling is really weak, and I want to improve that. And if you want to write some code, please let me know, because I've recently been pushing like a lot of changes and been reorganizing a lot of things. So if you have like specific requirements that I'm not meeting, and we can kind of agree that that's a good requirement, then I'll actually actively work with you to like either clean up the things that need to be cleaned up before you get there, or we can work together on it. Right now it's still a pretty small project. I've written all the code pretty much, and so there's a bus number of 1. And I would like to improve that. So this is the biggest takeaway. You should be doing this. There's no reason to lose more than a few minutes of data in all but the kind of most demanding high throughput environments, which most applications are not, even fairly big ones. There's absolutely no reason to lose more than a few minutes of data in the average case. And that is a standard that we aspire to at Heroku. Well, actually, we aspire to a higher standard, but we haven't gotten around to implementing it yet. But in the end, you need to meet it or beat it. At this point, save something like a very obscure Postgres recovery bug or operator error, which I try to minimize through tool design. There's no reason for anyone on Heroku to lose more than a few minutes of data. And that's something that we're very proud of, and we continue to invest in our durability, because even for your Web 2.0 startup, losing your data, especially even a day's worth of data, is a pretty big deal. It's not even for a non-bank entity. Losing a day is a really bad day. If you lose 5 minutes, banks would probably be unhappy, but a lot of people are ecstatic that they survived a total RAID failure losing 5 minutes of data. So that's it. I'm now opening myself up for abuse and questions.
Backup push, does that have the ability to limit the bandwidth?
It does. There's a feature called cluster rate limit that does actually let you limit the bandwidth to like 10 megabytes per second or something like that.
Would that also affect, basically what I'm thinking is I'd like to send WAL files as fast as I can, but if I'm trying to do that and then also trying to push a new base backup, that obviously there could be some conflict there.
Yeah, there could be conflicts. I might have tried a control daemon, but I wasn't playing. Let's see. WAL segments, at least in the environment that we're on, and it'd be interesting to see if this holds, they can only be produced so fast because, quite frankly, network block devices kind of suck. They're okay for a lot of things, but compared to your big iron, they're not going to write too fast. So far, backlog's not been a problem. However, it would be totally reasonable if you said, hey, if there's a lot of WAL backlog and we actually have a little query that we monitor. That's one thing you have to monitor is WAL backlog. It doesn't usually happen, but there's a little query that using some, which we can share, that just counts how many things are in archive status done versus ready, and then we have a pager alert set on some sensible threshold. But if you want to have some extra smarts to avoid stealing some bandwidth, then you can. However, backlogs are practically zero, 99% of the time, in our experience.
Do you know what the highest WAL segment creation rate is?
Well, it's sequentially written, which is actually really nice because you can still use magnetic media on the WAL drive very productively. And that, if your disk can write 70 megabytes per second, that's as fast as it can go. In the future, we do want to implement some sort of back pressure that's more official, because we do not want people to get too far ahead of the archiver. But probably before we do that, I'm just going to parallelize the archiver, and then it'll be blazing fast, and then nobody will care very much for quite a while, I hope. Yeah, these are theoretical problems, but so far, especially if you're using AWS, which is our use case, it's not something that usually happens.
I was just concerned because I know that at peak we could generate even more than one WAL file a second. So.
We've seen some we've been there. We can definitely hit more than one WAL file per second. I think we've seen at least one instance that we monitored closely that had 20 or 30 megabytes of throughput per second. So that one was very sensitive to particular hiccups in the S3 availability or speed, which is interesting. So we got to have this little tripwire. One reason why I want to make it a little more robust is databases near the edge might need a little more parallelism. But usually works. I wouldn't necessarily take something that you already have that's working and switch immediately. But if you're not doing anything, which actually seems to be the common thing because it's a pain, stop doing nothing and start doing this. That's what I would say is the best target audience. Any other questions? No details about, like, you know, have anyone read the README and said, wow, this is crap?
Well, it is written in Python.
Actually, as an interesting aside, it's actually using gevent. What is it?
Given that I've been using pgrman, which is written in C, but I prefer Python if I have to tweak the way that it operates.
I mean, I would really invite contributions and suggestions. I mean, I have some users in the wild. One of them even hacked in like a kind of a quasi-archive command to encrypt with GPG. And I would actually like to adopt kind of an archive command overlay instead of just saying, well, LZO is all you get. I want to say, well, you put it into a command and it can use your GPG keychain or whatever. So I do want to get there. This tool still has a lot of areas it can improve, both in user friendliness and speed and extensibility that would be important to us. It also uses gevent. Have you ever used, any of you used gevent or heard of it on Python? It's all coroutine based, so it's non-blocking I/O, but you don't actually write non-blocking style code. It's very cool. All right, going once. Going twice. Sold to Josh Burgess.